Hello and welcome. Welcome to this webinar series on applications of remote sensing based evapotranspiration data products for agricultural and water resources management. My name is Amita Mehta and this webinar series is organized by NASA's Applied Remote Sensing Training Program. Before we start with today's session, here are some prerequisites. There are 3 sessions on ARSET website. They provide information about fundamentals of remote sensing, including NASA's Earth Observing Fleet and also remote sensing for water resources management. Also, there is an introductory webinar that was offered a number of years ago that provides information about remote sensing of evapotranspiration and some fundamental definitions about evapotranspirations. So just to start with, what is evapotranspiration? We already know it is really sum of evaporation from land surface and transpiration from plants. Evapotranspiration or ET, it transfers water from land surface to atmosphere in vapor form, and that requires energy to convert that liquid to vapor. ET is important because it's critical component of the water and energy balance of climate soil vegetation interactions. It is also useful for determining agricultural water consumption, assessing drought conditions, developing water budgets, monitoring aquifer depletion, and monitoring crops and carbon budgets. However, it is challenging to measure ET. As shown here, first of all, it is highly variable in space because it depends on many variables, including solar radiation at the surface, that's the energy required to evaporate water, land and air temperatures at the surface, humidity, surface winds, soil conditions, vegetation cover, and types. All these are required. So measuring ET is challenging, and it is basically estimated from combinations of observations and models. And that brings us to our training objectives for this webinar series. So by the end of this training, we will be able to identify state-of-the-art techniques to derive ET using remote sensing, recognize how ET data can be used in water resources and agricultural management, and access OpenET and EcoStress data products for applications. OpenET is a data product derived from multiple satellites, and EcoStress ET is a product that is derived from EcoStress sensor observations which are taken from NASA's International Space Station. The training outline is given here. There will be 3 sessions, each 1.5 hours long, and they will be offered in English with materials available in Spanish. Today's session will be about OpenET, and it will be presented by Forrest Melton from NASA Ames Research Center. Second session will be on June 8th, and that will focus on EcoStress ET, and that information will be provided by Gregory Halverson from NASA JPL. The final session on June 15th will have exercises where we will have instructions how to access and analyze OpenET and EcoStress ET data products. Today's outline is given here. We'll start with information about ARSET program, and then Forrest Melton will talk about OpenET, focusing on data products, data portal, and applications. There will be one homework assignment given at the end of this webinar series on 15th of June, and answers must be submitted via Google form accessed from ARSET website. The homework will be due on June 29th, 2022. A certificate of completion will be awarded to those who attend all live webinars, complete the homework assignment by the deadline, And then you will receive the certificate from Marinas Martins in about 2 months period after the completion of the course. We'll have some information about ARSET for those of you who are new. Applied Remote Sensing Training Program, or ARSET, is part of NASA's Applied Sciences Capacity Building Program. For more than 10 years, ARSET has been empowering the global community through online and in-person remote sensing trainings in these thematic areas. So water resources, air quality, disasters, land, and climate, which is recently added to our training. ARSET's goal is to increase the use of remote sensing and earth science modeling data in decision making through trainings for professionals in the public and private sector, environmental managers, and policymakers. All ARSET training materials are freely available to use and can be adapted for your curriculum. If you use the methods and data presented in ARSET trainings, please acknowledge the NASA Applied Remote Sensing Training Program. And here's the website where a lot of information and all the training material can be found. So that brings us to our today's session about OpenET, data products, data portal, and applications. And we invite Forrest Melton to provide this information. Forrest Melton is a senior research scientist with the NASA Ames Cooperative for Research in Earth Science and Technology and California State University, Monterey Bay. Forrest currently serves as the program scientist for the NASA Western Water Application Office and as an associate program manager for the NASA Earth Science Applied Sciences Water Resources Program. Forrest has worked on the development of modeling and data assimilation frameworks, including the Satellite Irrigation Management Support, or SEAMS, system, the Terrestrial Observation and Prediction System, TOPS, and NASA Earth Exchange, or NEX. He received the NASA Exceptional Public Service Medal earlier this year for his efforts in the availability of satellite data for a range of applications. His research interests include remote sensing of evapotranspiration and agricultural water management. He serves as the project scientist for OpenET, a multi-institute project to provide evapotranspiration data products derived from remote sensing. So here's Forrest.
Thanks, Mita. Really appreciate the opportunity to talk with all of you and to be here on behalf of the OpenET team. I'm really proud of what the OpenET team, the consortium, has accomplished over the last 5 years, and I'll be talking through all of that today. I'm going to turn my camera off while I present, and then I'll turn my camera back on at the end as we transition to questions. So every day, thousands of people across the West are making decisions about water. So that might be an irrigator, ranch manager, or farmer waking up at 4:30 or 5 in the morning to turn on a pump or open a valve, all the way up to local, state, and federal water planners developing and working on solutions for some of the longstanding challenges for water resources management in the Western U.S. And many of them are being asked to find ways to do more and more with less. This makes good data information all that much more important. And until recently, many of these decision makers lacked one of the most important pieces of information for water resources management, which is timely, consistent information on evapotranspiration, the amount of water that's being consumed by crops and other vegetation as they grow. OpenET has been working to address this data gap. And with the launch of the Data Explorer, OpenET began to deliver daily, monthly, and annual information on evapotranspiration at the scale of individual agricultural fields for the 17 Western states. We brought together the scientific community behind different approaches for mapping ET with satellite data, and have been using best available science to make consistent, near real-time, field-scale ET data easily accessible for any location in the Western U.S. In addition to providing the data summarized for individual fields across the West, information is also available at the original satellite resolution of 30 meters by 30 meters. And data is currently available through the Data Explorer for the previous 5 years as well as the current year. And I'll provide a demo of the OpenET Data Explorer and talk about the other components of the OpenET architecture here in just a little bit. And just as a level set for evapotranspiration, it's important to consider that, of course, water applied to a field ultimately goes to a couple of different places. It can evaporate or transpire, and those two pieces together are evapotranspiration. So this is the total amount of water being used by crops and other vegetation as they grow. In contrast, some of the other places where water can go, including recharging underlying groundwater, or water, some of it might run off and return to a local canal or river. That water is often available for reuse, either downstream or in the future for other purposes within the basin. But the information that's consumed through evapotranspiration, that is no longer available for other uses in the basin. That's removed from the water supply and is often referred to as consumptive use. And what's challenging about evapotranspiration is that it's happening all around us all the time. It's the second largest component of the water cycle in most water basins. But because water vapor returns to the atmosphere as water vapor, it's invisible, we can't see it, and it's really difficult and expensive to measure on the ground. So as you can see a screenshot here, sometimes when you wake up early in the morning and the atmospheric conditions are just right, you'll see as the sun comes up, it'll heat the soil. We'll see that in this case, evaporation start to occur from the soil. And if the air is cool and it's been a cold night the night before, clear night the night before, sometimes that water vapor will condense. And so we'll see that process of evapotranspiration for just a moment until the air warms up. But it's important to consider that that is happening all around us all the time. And again, really difficult and expensive to measure on the ground. So what I'll talk about today is I'll provide an overview of OpenET and talk a little bit about the value of open data and our objectives, say a bit about how OpenET works and provide a demo of OpenET. We'll provide a short summary of the accuracy assessment and intercomparison work that's been done for OpenET. We'll spend some time talking about the use cases and pilot projects that OpenET has been conducting, and then wrap up with some next steps for OpenET and lessons learned. I'll also say a little bit about the NASA Western Water Applications Office and the NASA Applied Sciences Program. So first up, OpenET and the value of open data. OpenET has been founded on open science and has really been a community-driven effort from the beginning. We've brought together many of the science teams that have been working in some cases for decades to develop capabilities to map evapotranspiration across the landscape using satellite data. We have currently implemented 6 different approaches for mapping evapotranspiration from satellite data on Earth Engine as a shared computing platform. And this has allowed the team both to make progress on developing consistent approaches for the way we ingest and pre-process the satellite and meteorological inputs, to work together on a joint accuracy assessment and intercomparison study, and then also to make improvements in the individual models and approaches used. One of the key barriers to more widespread use of satellite-based ET data in the past has been the availability from different sources of ET data. And by bringing them together, it allows practitioners to easily compare the different estimates. The OpenET team is also providing a single ensemble value, which I'll talk about. The goals for OpenET have been from the beginning to produce reliable and easily accessible ET information that can be accessed for all farmers, communities, and water managers in the Western U.S. That the data is seen as trusted, it is being used by farmers and public resource managers at local, state, and federal levels, and that it is supporting the implementation and adoption of a variety of innovative and locally driven water management practices at scales that have not previously been possible. OpenET is committed to providing equal access to information, so regardless of the technical capacity or financial resources of users, we want to make sure that there is equal access to this information and that it can serve as a shared basis for decision making, planning, and development of solutions that are locally driven and in basins across the West. As I mentioned, OpenET is using these 6 well-established methods for calculating ET from satellite data. Our criteria for selecting these different approaches is one, that the teams were interested in making the data widely available and making the models available as open source software as the current versions are completed and prepared for open source software release. And that second, that the models were either in use by a state or federal agency or advancing towards operational use by a state or federal agency in the West. And so we've been lucky to bring together many of the leaders in the field of remote sensing of ET in the US to work together to develop the OpenET platform and data resources. And as I talked about earlier, one of the things that OpenET allows you to do is to easily compare the estimates from these different sources just by literally the click of a mouse. In addition, we are providing this ensemble value. And the way we're doing this is we're calculating the median absolute deviation and using that to identify and filter outliers. Once that has been completed, next we are then calculating the ensemble value as the mean of the remaining models in the ensemble after the outliers have been detected and removed. Now, in our intercomparison and accuracy assessment, the ensemble value has performed as well or better than any individual model across just about every measure of accuracy. However, we understand that for certain crops, for certain locations, particular meteorological conditions, there may be one model that does particularly well. And so we are working with partners right now on additional assessments to see if there are some locations where we need to recommend perhaps 1, 2, or 3, a smaller subset of the overall ensemble for use for, again, for particular crops, locations, or meteorological conditions. So how OpenET works? Well, for that, first let me go ahead and provide a short demo of the Data Explorer. And so one of the very first things you'll notice when you visit OpenET is you'll have the options to view the gridded data. Again, this is at the original satellite resolution, 30 meters by 30 meters, or just about 1/4 of an acre per pixel for any location in the Western US. Data has also been pre-computed from data summaries have been pre-computed for millions of agricultural fields across the West. Information can be selected for the current year as well as any of the last 5 years. Information is available for ET, NDVI. You can toggle back and forth between millimeters and inches, whatever is more comfortable for you to work in. And then information can also be added to assist with identification of particular locations of interest and for navigation. The colors here correspond to the legend. Just by toggling over the legend, putting your cursor over the legend, you can get the values displayed that correspond with each of these colors. So I'm going to go ahead and to show the full functionality of OpenET, look at a field in Grand Valley, Colorado. And you'll notice that once I get in beyond about zoom level 12, just by placing my cursor over a field, it will provide information on the total annual ET for the year selected, the area of the polygon and the field boundary, the crop type. And if I go ahead and click on a field, this is actually going to make a live call out to our geodatabase and retrieve the time series of information for that field. Each of the data points in this time series represents the total monthly ET. In this case, I'm in English units, so that's going to be displayed in inches. And the volume of water in the ET as a volume of water will also be available there as acre feet. But what I'm seeing here, so for example, looking at in July of 2020 for this field, an ET rate of just about 6.5 inches. And that's about what I would expect for a well-watered alfalfa field in this location. Again, I can also look at the range as a measure of the uncertainty across the ensemble and turn on information and time series for any of the individual models so I can compare them. So if a producer or engineer or hydrologist at a state or local agency has worked with any of these models, they can, in the past, they can easily compare them to estimates from the full ensemble. Information is also available for additional ancillary layers, ET fraction, reference ET, and MDVI. Now, in addition, we can also, in addition to looking at the time series of monthly data, we can also look at this as cumulative annual totals, and we can compare the ET from different years. And one of the reasons I selected this field is that it was enrolled in a voluntary incentive-based conservation pilot program that was evaluating changes in total evapotranspiration and consumptive use associated with different irrigation management practices. And we can see, looking both at the monthly time series, 2017 and 2018 stand out as looking a bit different from the other years. And we can see that clearly in the cumulative total. In 2017, this field was fully fallowed, and we can see that the ET dropped from about 32 to 38 inches per year, all the way down to just a little under 6.5 inches. So by fallowing this field, we get a significant reduction in total consumptive use. Ideally, we'd like to be able to sustain agricultural production while also providing, during times of drought, also allowing the incentive-based programs to support continued production. And so we see 2018, what they tried was putting on the water a little bit late in the season, giving up that first cutting of alfalfa, but still able to harvest a crop later in the year. And we can see that that still resulted in a pretty meaningful, roughly 30% reduction in total ET and consumptive use. So this ability for the agricultural producer, the landowner, a program administrator to all be looking at the same information at the same time to evaluate how different changes in irrigation practices at the field scale affect ET and consumptive use is particularly powerful in thinking about how we quantify these changes in ET and how we can scale different types of programs to accelerate water conservation. The other thing I want to highlight here is that data can also be queried for any location. So if we wanted to compare ET estimates within the field against adjacent areas, some of the non-irrigated grasslands, we can easily do that. If a user wanted to select an area for which there wasn't a boundary, perhaps for a wetland area, upland forest, non-irrigated grassland, or to just look at a portion of a field, we can do that too. So by clicking on the Draw Custom Area tools, you can then select any location of interest. This is actually going to go ahead and run a query against the full OpenET archive, hunt through hundreds of terabytes of data to find the data that's of interest. It's compiling that, and it will return the summaries here. There it goes. And then again, just showing the ensemble ET value, both as the monthly time series and the cumulative totals. Daily data will be added here in just the next month or two. So daily information will also be available through this interface. And again, queries can be executed for any location in the Western US. I should emphasize that the Data Explorer was designed to really make it easy to begin to interact with and explore the data, retrieve locations for any location of interest just using a web browser. This is intended as the first piece of the OpenET architecture. Later this year, we'll also be publicly releasing the API, the application programming interface, as well as custom reporting tools that will allow users to not only draw these polygons, but also save them, upload shapefiles, and get ongoing reports for regions of interest and locations, whether that's an individual farm or ranch or a watershed. So there's a couple of important considerations to keep in mind when you're working with data from OpenET. First is that OpenET provides information on the total amount of water consumed through evapotranspiration. So this is going to include the ET from irrigation, from applied water, from precipitation, and even access to shallow groundwater. And so if you are comparing data from OpenET to measures of applied irrigation water, typically from a flow meter, it is important to at least subtract off the effective precipitation first before making that comparison, right? Because again, the meter is going to be measuring the total amount of water applied, and data from OpenET will include information on ET both from the irrigation as well as from any precipitation that occurred on that field or that region. Second, the crop type information available on OpenET, as well as the field boundaries. It's all from publicly available data sets. And the crop type information is really there to assist with interpretation of the data. If there's any errors, those do not affect the accuracy of the ensemble ET value. And then third, the relationship between evapotranspiration and crop water requirements can be complex. Different types of crops, different crops grown in the same crop grown in a different region, they can require different amounts of irrigation and different amounts of ET for a number of factors, everything from differences in soil type and texture, different planting configurations, different salinity management considerations, and other production factors that the irrigator, the ranch manager, the agriculture producer all have to account for. Another important consideration is that OpenET data do not represent direct measurements of evapotranspiration. They are calculations based on satellite meteorological, soil, and vegetation data sets. They are used within state-of-the-art vegetation models, and while the OpenET team considers them to generally be accurate and consistent, we know they have limitations. So especially during times of consistent and dense cloud cover or areas with complex topography, we would expect the uncertainty to be higher in these situations. At a high level, OpenET is driven entirely with publicly available satellite and meteorological data. That information is brought together on Google Earth Engine, which is a cloud computing platform optimized really for geospatial analysis. And all the models are run there. Google Earth Engine makes it much easier for the teams to collaborate on the development of consistent pre-processing and ingestion, algorithms and workflows for the satellite and meteorological data. The pre-computed summaries for the individual fields are stored in a geodatabase. We are working with the application programming interface is currently being tested and prepared for public release later this year. And then we just walked through the Data Explorer, which is now publicly available, and again is intended to facilitate interaction, engagement, and exploration of the data for a lot of the scientific uses and integration with other tools. We expect the API to be the primary way, the API and the custom reporting tools to be the primary way that users will interact with the data. And we're developing the API because we know that ET information is often most valuable when it's combined with other sources of information. So whether that is software for irrigation and nutrient management or other farm and ranch software management software applications, whether those are water data informations maintained at local, state, federal, and tribal agencies, or water trading and water accounting platforms that are being developed in irrigation districts and watersheds across the West. The OpenET application programming interface is built following the OpenAPI specifications. The screenshots here, examples of the documentation and the various endpoints. So we include endpoints for retrieving metadata, for retrieving subsets of the raster data sets, and for retrieving subsets from the geodatabase time series for particular fields or locations of interest. Again, that will be available later during the second half of this year. So currently being tested by getting close to about 200 partners and being prepared for that public release as soon as we can have everything completed and documented. And the OpenET custom reporting tools, those are also under development. These are being developed to ensure that folks are able to access and retrieve information from OpenET regardless of the technical resources available to the user, and to allow folks with a web browser to get access, again, for any locations and time periods of interest. The integration with other tools for irrigation management are particularly important. We know that when managing water at field scales, irrigators and agricultural producers have to account for a range of factors. So they have to consider not only the weather data and evapotranspiration rates, but also information on targets for leaching fraction, the irrigation type and application rate, distribution uniformity, soil type and texture. And so partners at Cooperative Extension and in the commercial sector are already developing software tools to support growers in taking weather information and ET information and translating those into irrigation system runtimes. And so we've developed the API in large part to make it easier for these types of existing tools and tools that are being developed to retrieve and integrate satellite-based information on evapotranspiration into these applications and make it available to irrigators, branch managers, and agricultural producers in the field where and when they need it. OpenET is driven with data from a constellation of satellites. So we use data from Landsat, from the Terra and Aqua satellites, from the NASA NOAA SUMI MPP mission, the NOAA GOES satellites. We're working on integrating data from the Sentinel-2 mission, operated by the European Space Agency. That said, Landsat has really been the workhorse. It is the satellite that provides the concurrent optical and thermal measurements at that 30 to 100 meter resolution that allows us to produce the field scale ET data. So the key principle behind remote sensing of evapotranspiration is that evapotranspiration consumes energy. And this is going to be familiar to anyone who's run through a sprinkler on a hot summer day. Run through the sprinkler. After you do that, of course, the water is going to evaporate from your skin. That's going to consume energy, cool your skin. And that same process occurs across the landscape. And the way that shows up in satellite data is that areas with higher rates of evapotranspiration, I mean there's more energy being consumed, are going to appear cooler in the satellite imagery. And conversely, areas with less evapotranspiration are going to appear warmer. And we can measure that with a thermal infrared sensor on Landsat. And so as Landsat is orbiting the Earth, it's measuring thermal infrared emissions. And we're seeing the areas with higher land surface temperatures, those are typically going to be associated with areas with lower rates of evapotranspiration. And the cooler areas are going to be associated with higher rates of evapotranspiration. Landsat also provides us with the measurements in the optical wavelengths, and in particular, we use measurements in the near infrared and red wavelengths. Landsat is measuring the amount of light being reflected off the land surface in these key wavelengths that help us calculate measures of vegetation density and condition that are also important inputs to many of the ET models. So to give you a better sense of what the satellite sees, I got 2 basil plants and I put one in the oven for about an hour to simulate a flash drought. And then I took the camera off of our UAV, and this is a camera that measures some of the same wavelengths that Landsat measures. And you can see how different these 2 plants look. So in the center image, you're seeing the difference in the thermal infrared emissions, and just see how much cooler the well-watered plant looks. And then on the right, you can see the difference in the normalized difference vegetation index, which is computed from the red and near infrared wavelengths. And it is this commonly used measure, remote sensing measure of plant density and condition, vegetation density and condition. And then zooming back out to look at this at the same scale that Landsat sees, we can see on the left, this is what the landscape looks like in a true color image combining red, green, and blue wavelengths. In the middle there, we see the thermal infrared emissions, and we can get a really clear sense as to just how much cooler those well-watered center pivots look. And then on the right, again, where we have healthy, well-established crops, we can see the NDVI looking a lot greener, reflecting much higher density of vegetation and a strong signal that we've got healthy, well-watered vegetation there across that landscape. Now, I could spend probably the whole hour and a half just on this slide, but it's worth mentioning that there are two primary approaches used to quantifying evapotranspiration with satellite data. The first is the energy balance approach, and in this approach, what the models are doing is computing the different components of the surface energy balance to calculate evapotranspiration, or the latent energy, as a flux, as a residual of the surface energy balance. And so we know that incoming solar radiation, the RN term, or the incoming solar radiation has got to go somewhere. It can be reflected back out to space. And so the difference between what's coming in and what's reflected is the net radiation, the RN. It can go to heat the ground surface, that's the G, the ground heat flux, or it can heat the air, and that's the sensible heat flux, that H term. And what's left has got to be the latent energy flux, the amount of energy that's being consumed by evapotranspiration. And so the models have different approaches for computing these terms. They share a lot of commonalities in the computation of the net radiation and the ground heat flux, and where they take very different approaches is in how they compute the sensible heat flux. And so they'll combine different meteorological products, many of them all driven with Landsat data. And they'll also incorporate, and some of them will incorporate satellite measurements from other platforms, like GOES. But at the end of the day, what they're doing is calculating ET by solving the surface energy balance. The second category of approaches, I would consider reflectance-based approaches. And these approaches typically are assuming that vegetation over agricultural landscapes is well watered, and they'll be using surface reflectance information typically to compute some type of vegetation index. In this instance, we're showing the normalized difference vegetation index, which is used by SIMS, which is one of the reflectance-based approaches that's incorporated into the OpenET platform. The SIMS model takes the approach of first translating NDVI into a measure of the effective fractional cover. It then incorporates information to calculate the effective canopy density and shading to compute a max relative evapotranspiration rate. It accounts for crop height. And then it computes this density coefficient approach and uses the density coefficient to then index into a set of equations that were developed by Rick Allen and Luis Pereira originally to compute a crop coefficient for every 30-meter pixel that accounts for the current crop growth stage and condition. It then brings in information on reference ET from different gridded meteorological products or from agricultural weather stations to compute ET following the FAO 56 approach. SIMS has also been updated to incorporate information on soil evaporation from precipitation using a gridded soil water balance model. But most of these reflectance-based approaches are assuming that vegetation is typically well watered. One of the main limitations of these approaches is that they are less sensitive to short-term and intermittent deficit irrigation and plant water stress. So next, I'd like to say a little bit about the work that's been done by the OpenET to characterize the accuracy of data from OpenET. OpenET has conducted the largest intercomparison and accuracy assessment to date for field-scale satellite-based ET data. We did this using a two-phase accuracy assessment approach. In phase one, we used information from 70 flux tower sites. This included 24 agricultural sites. The models were checked in and run before the data was shared with the teams. But after receiving the results, the teams had time to make improvements and updates to the models to account for any systematic biases that were observed. For some of these models, this was the first time they had been run at the scale of the Western US, so we wanted to give the teams an opportunity to adjust and correct, again, any consistent biases or issues with the models, as well as to address any bugs that were uncovered. In phase two, we added an additional 70 sites for 142 flux tower sites total. Again, models were run before the data was shared with the teams. Sites were implemented with full eddy covariance instrumentation. So the example of one of these towers is shown here on the right. Instrumentation for These towers typically cost in the range of about $50,000 per year and also require specialized expertise to maintain the instrumentation and process the data. An advantage of this full open path eddy covariance approach is that it also allows for independent checks on energy balance closure as an indication of the accuracy or uncertainty in the ground-based measurements. And so we were able to filter the ground-based ET time series to check for energy balance closure, to ensure that there were no more than 5 days per month that needed to be gap filled, also ensuring that there were maximum of 2 hours during the day and 4 hours at night that for each day that needed to be gap filled to any gaps in the 15-minute data record, 15 or 30-minute data record that is typically output from these stations. So the results here, we looked at a range of different accuracy metrics. We looked at different timescales, daily, monthly, growing season, and water year. We looked at both the slope and the mean bias error as different indicators of overall bias. For slope, of course, a slope of 1.0 would be perfect. For mean bias error, a bias error of 0 would indicate perfect agreement with the ground-based data. We looked at mean absolute error and root mean square error as measures of expected error. Mean absolute error is what we would think of as giving us our expected error on average for any given location or time for any given location. Root mean square error, another measure of expected error, but provides additional weight for outliers. So if there's an application that's especially sensitive to any large misses by the models, RMSE is a good measure to use. And then also included information on R squared as a measure of the ability of the model to reproduce the observed variability in the ground-based data set. Again, a score of, or a measure of 1.0 would be perfect. So just focusing on the mean absolute error, what we were seeing is that at an annual time step, typical errors of just under 9%. Growing season time step, errors of just over plus or minus 13.2%. A monthly time step, 16.6%, and daily just under plus or minus 23%. Now, the daily scale, we do start to get into some challenges in working with the ground-based data, just looking at, so we have different weather systems moving in. We'll know there'll be days where the satellite has measured conditions that were different from what the flux tower is seeing for any 24-hour period. We also know that there is higher uncertainty in the ground-based stations at the daily time step as well, just due to energy balance closure at shorter time scales. But overall, we were really pleased with these results. And the most important thing is that we're able to provide users with a characterization of the accuracy, both for this ensemble ET value, which is what we're looking at here, as well as for the individual models. The summaries of these results are available in a open access article that the team published in the Journal of American Water Resources Association last year, and then also on the OpenET website under the accuracy tab. Well, one other thing to mention is that when we looked at the average total growing season ET across all sites, so 38 sites where we had at least one full growing season, with a total of 151 growing seasons. When we looked at the average total ET from each of the models and compared it to the average ET across all of those flux towers, we saw that all but one of the models was within plus or minus 10% of the flux tower ET. All of them were within plus or minus 15%. A number of the models were within plus or minus 5%. So as we looked at across larger timescales and larger areas, we were seeing a lot of the errors condense, which is what we would expect if many of the errors were random errors. So this was also encouraging. I'd like to talk a little bit about some of the applications and use cases that OpenET has been supporting. OpenET has been user-driven from the very beginning. OpenET has been built around use cases and received input from more than 100 partners in the water resources management and agricultural communities. Just about anything that's part of the OpenET API or the OpenET Data Explorer is there because one of our partners has requested it. OpenET can help with a number of key applications of satellite data for water resources management. In particular, OpenET can support rural communities in designing locally driven water conservation and trading programs that are informed by satellite-based data. OpenET has value for assisting water managers in developing more accurate water budgets, which can then be used to create incentive programs and other innovative strategies to advance water conservation at scale across the West. OpenET can support policymakers in accurately tracking water supplies. Some of our use cases have focused on simplifying regulatory compliance and reducing costs for agricultural producers. And OpenET can assist policymakers in co-developing solutions with local communities. A lot of what we have focused on is identifying opportunities to use ET data to create win-win solutions where we both improve the understanding of water use within a region while also, and which can support advances in long-term sustainability of that water resource while also providing direct benefits back to the agricultural producers and water rights holders within a community. And then finally, and perhaps most importantly, OpenET data can support farmers in expanding the use of data-driven irrigation practices to continue to maximize crop per drop and reduce the cost to agricultural producers for fertilizer, water, and energy. These are some of the use cases that OpenET has been supporting over the last 3 to 4 years. And these span a range of applications and categories of use for OpenET. So we have use cases related to groundwater management, on-farm irrigation scheduling, applications focused on reducing regulatory costs for regulatory compliance, and then watershed scale management applications, as well as applications to support pilot programs for incentive-based water conservation and water trading. We have worked with small family farms, with some of the largest agricultural organizations in the West. Some of our use cases are supporting tribal communities, and some are supporting planting activities at the scale of the Upper Colorado River Basin. And while we don't have, well, it's almost impossible to have a full comprehensive suite of use cases, we've done our best to ensure that the use cases that OpenET has been supporting give us a representative cross-section of the potential applications in the long-term user community for OpenET. So I'd like to give you a chance to hear directly from some of our partners about what they see as the value of OpenET and how they're using it. First, we'd like to start with Mark Owens, who's a farmer alfalfa farmer in Harney County, Oregon, who's been using data from OpenET to inform his irrigation scheduling and management. And Mark's been helping us think through ways to make this data valuable for that type of application in Oregon and across the West.
We're under a drought in most of the West contiguously. The climate is changing. Summers are getting longer, it's getting hotter, it's getting drier, we're getting less precipitation. So I think there's a growing awareness in all of the West that we have to use significantly less water. So agriculture has to figure out how to get as much per drop of water as they can. I started to try to understand evapotranspiration when we collectively started trying to figure out, can I put less water on my fields and still yield the same amount or more? I go online and I can pull up the evapotranspiration numbers. I compare the amount of water that I apply daily, weekly, probably monthly, compared to what OpenET says, and I can see if I'm over-applying or under-applying. So if I put on more water than evapotranspiration I already have in my bank, I can shut off for a couple days. That means we could use about 25% less water and still produce the same amount of crop, which means a lot if you're putting out several million gallons of water a day.
Second use case I'd like to highlight is work with the Rosedale Rio Bravo Water Storage District. They have been working to develop a groundwater sustainability plan in response to the passage of the Sustainable Groundwater Management Act in California. And what they have been doing with OpenET is using that as an input to their water accounting platform that's been developed for agricultural producers within the Rosedale Rio Bravo Water Storage District. OpenET has served as the basis for that accounting platform and will support the development of water trading programs within the water storage district in the future. And I'll let Eric Everett, who's the former general manager for Rosedale Rio Bravo, describe that.
Rosedale is located in Kern County. It's one of a number of water districts that provides both agricultural as well as urban water supplies. Kern County is considered ground zero in the context of the Sustainable Groundwater Management Act. We have a significant amount of overdraft which challenges the water supply reliability for the region. The OpenET data set that we will be using is the basis of our water budget for Rosedale, which will be reported to the state to show compliance with the Sustainable Groundwater Management Act. For the landowner, it's very, very important because they have now a responsibility to live within their water budget. OpenET has been a very, very effective tool, giving us near real-time information to evaluate the water budget information for every parcel within Rosedale. Landowners can make decisions as to whether or not they're going to irrigate again, whether or not they're going to enter the market as a buyer or a seller. And again, it's really information to make informed decisions, but more importantly, to manage the resource on their own behalf.
And then finally, OpenET is also being used for applications outside of irrigated agriculture. Of course, there are important applications for drought impact assessment, and for forestry management. In Arizona, we've been working with the Salt River Project to use data from OpenET to help them track and assess the impacts of different forest management practices on evapotranspiration and changes in the hydrology in the upper part of the watershed. And I'll let Elvie Barton describe that one.
We are in the East Clear Creek watershed. This is one of our most at-risk watersheds because our dam here is completely surrounded by ponderosa pine forest that are in an unhealthy state. With increasing temperatures, we're having increasing variability with droughts, and unhealthy forest has fuel for large catastrophic wildfires. So we adopted a 2035 goal to support 500,000 acres of forest thinning. Now this is unprecedented since no utility in the United States has taken on a forest health goal. It's going to take a lot of science and tech and data. And so when we begin our forest thinning projects, the trees will become more drought tolerant. OpenET will help us have data to inform how our forest thinning projects are reacting to those climate change impacts that we're seeing today.
Okay, so what's next for OpenET? First, as I mentioned earlier, we will soon be releasing daily data through the Data Explorer, as well as through the Application Programming Interface, the API. And we'll be focused heavily over the next year on integration of those daily data products with irrigation scheduling tools, working with our partners at extension agencies and in the commercial sector. As I mentioned earlier, we are working towards the public release of the API in the second half of 2022. And that will coincide with addition of the OpenET data for 2016 through 2020 to the public data catalog on Earth Engine. So for those of you who are interested in OpenET for research applications and looking to access large subsets of the data, that will be the best way to work with the information. And I'd recommend that you sign up for the newsletter and mailing list at openetdata.org, and we will be notifying all users of OpenET when the API is available and when the data for 2016 through 2020 has been added to the public data catalog. We will also be working during the second half of this year on completion of the custom reporting tools that I showed briefly. Again, that'll be an important component to allow folks to set up areas of interest, upload shape files, draw and set field boundaries, and then get ongoing reports for those locations of interest. Also working on a best practices manual describing recommendations for use of the ensemble ET value, as well as data from the individual models for different water resource management applications. And I may have forgotten to mention, but we are also currently completing updates, the final runs of all models for OpenET Collection 2. So as soon as that's ready, we'll be working on pivoting towards completing the best practices manual. And we have additional work to do for the science team. That's going to include evaluating the models for some particular situations, including well-established mature tree crops, identifying which models perform well for that, not just that particular crop type, but that particular stage of crop production. Those well-established orchards where we can have shading of the interrow during the time, typically during the time of the landside overpass. Also working on improved approaches for open water evaporation and evaluation of the ET estimates from the different models over open water, over lakes and reservoirs. And then also continuing to develop and improve the models for forests and other non-agricultural landscapes. And then another last major piece on our roadmap here is developing workflows to automate the calculation of effective precipitation so we can compute ET of applied water across the West. I would like to close with a few lessons learned, from OpenET, and then also talk a little bit about the role of the NASA Western Water Applications Office in the NASA Applied Sciences program. First, especially when you're introducing a new water data set, important to understand that new water data can be sensitive. And it's important to listen to concerns from all stakeholders. Within the OpenET consortium, we have really prioritized the identification of win-win solutions where there are clear benefits to individual agriculture producers from the use of ET data, while also improving our ability to understand total use of water through ET in a particular location or a particular watershed, and improving the accessibility of information on evapotranspiration to water resource managers. Second, open science and open data are not free. So important to keep in mind that free to the user does not always equate to free to the provider. So for those of you that are also working on other applications and are working hard on open science activities and trying to increase access and the usability of information on water, it's really important to plan far ahead and think about the long-term sustainability of the data resources and compute resources that you'll be using. We've done our best to start early, but still nothing will ever go according to plan. If that happens to you, just know that we feel your pain. And then finally, the user-driven design process really works if time allows. This is something that OpenET has underscored. We started with a series of workshops and public meetings and small working groups. The sketch on the left is that was my original sketch for OpenET, for our architecture. That was the simple cartoon schematic. And this is where we've wound up. And I cannot express much how proud I am of this team, and I think that what's been designed and developed really establishes an important milestone in terms of our ability to easily distribute satellite-based information on evapotranspiration for any location in the Western U.S. to any user with an internet connection app and a web browser. So really tremendously proud of what the team has been able to accomplish over the past 5 years. Oh, and then finally, partnerships matter. None of this would have been possible without a team of really dedicated scientists and software engineers from 3 federal agencies, 7 universities, working with the Environmental Defense Fund and Google Earth Engine. So, and then, of course, Habitat 7. They did a phenomenal job with the web design and a lot of the software engineering for the Data Explorer. And so NASA's role in this, of course, is twofold. NASA does operate a large fleet of Earth-observing satellites. These satellites provide insights to almost every component of the Earth system. Data from NASA is freely, and from all of these satellite missions, is freely and publicly available. And the NASA Applied Sciences program is then tasked with translating NASA's scientific and technical advances into societal benefits. Within the Western U.S., the NASA Western Water Applications Office is specifically focused on identifying ways that we can support water resources managers in applying NASA data, technology, and tools to support decision-making for water resources management in the Western U.S. We do this by identifying the needs through working groups and needs assessments. We then work hard to establish connections between our water resource management and agricultural partners with NASA scientists and folks at NASA centers and our NASA-supported science community, and then provide support for projects tailored to address those needs, engaging users from the beginning, as OpenET has done. And then longer-term work to transition those applications or find ways to sustain them long-term so that they'll provide a reliable information resource for water resources management for the foreseeable future. And so if you have questions, please don't hesitate to reach out to me. I will note that OpenET is currently focused on providing data for the Western U.S., working on plans to support expansion to cover at least the CONUS, the lower 48 states. Longer term, considering strategies for ways that we can work with international partners to support expansion for areas around the world where ET data would also be valuable. But at least for the next 12 months, we'll probably be focused on the U.S. So with that, if you have questions, happy to try to answer a few of those now. Can also contact me here, or we'll also encourage you to send questions to support@openetdata.org. That will be one of the best ways to get answers if you have questions about OpenET in particular. So thank you so much for listening. Really appreciate your time and attention, and happy to answer any questions. Back to you, Anita.
Thank you so much, Forrest. I mean, that was just a wonderful talk, and I think we really learned so much, not just about ET, but there's an open source data with multiple products. You also showed some very useful case studies that we always get requests from our ARSET participants that they want to see how data are actually used in real life applications. So this was really great, and thank you so much for the information and your time. And next we have a question answer session. You can type your questions in the QA box. Some of you have already done so, and Forrest is here to answer some of the questions. And we will be posting this Q&A document on our website. So before we switch to QA, here is the contact information again. You can contact Forrest Melton for more information about OpenET, and any general questions about this training, you can email me. Here's the training webpage where you will have all the slides available, as well as the recording of this video will be posted there too. And this is the ARSET website, and here's the Twitter feed for ARSET. With that, let's start with question answer session.
Before we jump in, could I also ask you to add to that slide support@openetdata.org? Given the number, I'm really happy to see the amount of interest and number of folks who have joined the call. To handle the volume of inquiries we're receiving currently, we have set up support@openetdata.org to help us manage and respond to all the inquiries we receive.
Wonderful, thank you. So we'll start with questions which are already posted. First question is the OpenET database updated in real time?
Close to real time, yes. So currently the monthly, and Brock, I'll type in some of the answers for you there, I see, but it's close to real time. Monthly data is typically updated within 2 to 3 weeks after the end of the month. The daily data, it's available through the API, is currently updated typically within 3 to 8 days from the satellite overpass date. And we are testing a workflow to provide very low latency near real time daily data within 24 to 72 hours of satellite overpass.
Great. So second question here is the OpenET data available only in the USA, or if so, how can I study similar data in countries in Asia?
Sure. So yes, currently OpenET is just available for the 17 states in the western US. We're currently working on OpenET Data Collection 2.0, which will also include the Mississippi alluvial plain, and then we'll be working towards providing data for the rest of the US here over the next 12 to 18 months. We are starting to work on, I should have mentioned this at the end of my talk, we are starting to work with partners on some pilot activities in Brazil and Mexico to figure out how we can most efficiently scale OpenET to other areas where the data would be valuable around the world. Our approach to this has been to work with scientists in country and have them lead the development of any ET systems for their country or region. It is going to take us a little while before we can get to anything close to global scaling. There are other ET information products. You'll hear about EcoStress. I know ARSET has provided additional trainings on some of the other NASA ET data sets in the past. So there are other satellite-based ET data products for different regions in Asia.
Yes, that's correct. So if you look at the link of the evapotranspiration webinar we did a few years ago, it has some of the global data sets. Also, I think one thing to note here for us from your talk is that this project includes so many institutions and universities, so scientists and stakeholders and people who design the website and make it so easily interactive. I think that has to happen all over the world, and that's the difficult part and time consuming, I believe. So.
And doing the accuracy assessment, which is really important for a number of water resource management applications, being able to characterize the accuracy, that's a really important component of the project. Also, understanding, understanding the applications that would be most valuable and ways to utilize the data really requires local and regional expertise and folks with strong connections to agricultural producers and water resource managers in different regions around the world.
Yes, great. So question 3 is, how different or improved are the OpenET estimates from the dynamic global vegetation models or DGVMs?
We have not conducted any comparisons against the DGVMs. I would expect that a key advantage of OpenET, of course, is that the measurements from OpenET over irrigated agricultural lands are actually accounting for the evapotranspiration that occurs as a result of applied water. So we don't have to model or simulate irrigation the way that the DGVMs would have to do over irrigated agriculture. We're actually looking at the using the satellite data to either solve the energy balance or monitor the development of the crop canopy in terms of its density and condition. And so we're capturing that influence of irrigation directly using the satellite data, the combination of the optical and thermal information. But we have not conducted any comparisons yet between OpenET and the DGVMs.
So question 4, this is a great data tool. Will these data be available for use in Google Earth Engine? Is there a release date?
Yes, so we are starting to work on adding data from OpenET Collection 2 from 2016 through 2020. So that will be, over the summer, we'll be adding data from the models as the review of Collection 2 is complete to the Google Earth Engine public data catalog. Well, I should say that's planned. So we're submitting the request to Google to have them be added to the public data catalog. So we'll be starting with that initial collection and then continuing to add to it as we extend the data record back in time. Data for the most recent years will also continue to be available through the API while it's under review.
Okay, question 5 is, which model is the best for estimating ET while plotting against NDVI?
So yeah, good question. I'm not quite sure where that question is going. Let's see. The SIMS model, which is the model that's primarily driven with the reflectance data with NDVI, fractional cover using the density coefficient approach developed by Rick Allen and Luis Pereira, that's generally going to correlate most closely with NDVI. That said, all of the models will track the crop phenology measured by NDVI. The energy balance approaches will do a better job of capturing soil evaporation from bare soil, or soil evaporation from any fields where you have flooded fields like rice, for example, or flood irrigation of other crops early in the crop development cycle. But if you were looking to correlate a model with NDVI for a particular application, I would expect SIMS to track NDVI closely. And if there's a follow-up question, please add that to the chat. Happy to clarify.
Okay. So question 6 is, would you expect that OpenET could be useful to estimate evaporation in covers without vegetation, so open water or moist, dry soil, covered or not, stubble from previous crops? How would you expect OpenET to perform with other vegetation types, not crops like dry forests?
Sure. Yes, definitely. So OpenET should definitely be useful for capturing evapotranspiration from areas, wet, bare, wet soil, stubble from previous crops. The energy balance approach is basically the models, except for SIMS, should all do well in that situation. And the ensemble ET value should also provide a reasonable estimate. At those lower, typically we have lower ET in those conditions, that you'll see a larger range across the ensemble. And so as a percent of the overall absolute ET value, we'll expect higher uncertainty. In terms of the absolute error, since the ET values are typically smaller, we would generally expect lower absolute error, but higher percent error. Open water is a harder problem. So Hulan Gao at Texas A&M is currently leading a project focused specifically on using satellite data to quantify evaporation from open water. There are initial estimates there from some models for open water in OpenET. We have not just had access to the data resources to really fully quantify the accuracy of those estimates yet. So if you use those, I would just assume a higher overall uncertainty over open water, and really looking forward to seeing what Hulan Gao and her team will be able to accomplish in advancing our ability to quantify evaporation from open water from lakes and reservoirs. For other vegetation types, yes, we have also, out of those 142 flux tower sites, 72 were non-agricultural. In general, the uncertainties are a little bit higher than they are for irrigated agricultural land. So that, as I mentioned there in my talk, that'll be one of the key areas of focus for future research in terms of improving the overall accuracy for shrublands and upland forests. That manuscript is currently being written up and prepared for submission. So we will be adding information on the OpenET accuracy for other vegetation types in the near future. And there is additional information on the OpenET website at openetdata.org/accuracy.
So how is OpenET different from the MODIS ET product?
A couple of different ways. One, of course, and perhaps most importantly for a lot of agricultural applications, is the spatial resolution. So that 30-meter spatial resolution versus the 1 kilometer versus the coarser scale MODIS CT products. So that's a key difference. OpenET also includes an ensemble of models. So different approaches to solving the surface energy balance and using reflectance, surface reflectances to calculate ET. And then it provides that ensemble ET value computed from the 6 different models after filtering for outliers. So I'd say those are some of the key differences. We are conducting comparisons right now at those Flux Tower sites and incorporating the MODIS CT data set. We recognize that with the coarser resolution of MODIS, it's often harder to compare it to the Flux Tower measurements just because so much of this signal is coming from a footprint around the tower that represents just a portion of the MODIS CT pixel. But in general, we're seeing that for irrigated agricultural areas, the OpenET estimates provide a meaningful improvement in the accuracy. But we're still working through that full analysis.
Question 8 is, was there a separate accuracy assessment for non-croplands?
Yes, yeah. And so as I just mentioned, there were roughly half of the sites, about 72 of those towers were from non-agricultural lands, and we are currently writing up those results. So I think we've already talked about that answer to that question. But happy to clarify if there are any follow-up questions in the chat.
Question 9 is, do you apply surface energy budget closure correction to the Flux Tower ET estimates before comparing with the OpenET estimates?
Yes, yeah, great question. I should have mentioned that. Yes, we do apply an energy balance closure correction based on the energy balance ratio. We are also filtering. So we started with almost 300 Flux Tower records, and we filtered those to ensure that we had energy balance closure ratio of at least 0.75 during the growing season and 0.6 during the non-growing season. Details for that, the processing of the Flux Tower ET estimates are provided in the OpenET paper, Melton et al. 2021, that was published in the Journal of American Water Resources Association. That is an open access manuscript. So there's additional information on the energy balance closure correction there. There's also details in John Volk's paper, VOLK in 2021, where he described the automated software workflows used to process all of the Flux Tower data. That's available now as open source software. And then John's also just about to submit a manuscript describing the full Flux Tower data set that was used in the OpenET accuracy assessment.
Again, what's the resolution of the data?
The resolution of the gridded data products is 30 meters by 30 meters, which translates to 0.22 acres per pixel. So it's 30 meters by 30 meters.
Is it possible to get an insight into the algorithm used to generate data in OpenET?
Yes, so a couple of different ways. One, on the OpenET website, there's descriptions of the different models. There's links to the key papers describing the equations used within each model. Again, there's not a single algorithm. There's the 6 different satellite-driven models. To compute the ensemble ET value, we are using the median absolute deviation approach, taking 2.5 times that MAD value to define the range. Anything outside of that range is flagged as an outlier and removed, and then we compute the ensemble ET value as the mean of the remaining models. As I mentioned, one of the things we're working on for particular crop types and regions is checking to see if the performance of a single model or a subset of the ensemble will perform better than the current ensemble ET value. The long-term goal is to be able to take advantage of the strengths of each of the models to provide the most accurate overall ensemble ET value possible. In addition, we are working towards getting all of the models documented and available in open source software repositories. I know that there are repositories on GitHub for the CBOP model already, along with the GEE CBOL and SIMS, PTJPL, and Dyslexia are all close to being ready. think there should be an open source repo for SIMS, or if not, there will be very soon. So yes, so a couple different ways. Again, manuscripts available through the OpenET website for the major modeling approaches, and then working towards providing direct access to the model code through open source software repositories for the models used in OpenET.
Great. So do any other countries have anything similar to OpenET?
I know Australia has a similar system. I believe the model is based on an approach that's related to the approach used within SIMS. I would have to double check the latest. That's called ARSET. So I know Australia has a similar system called ARSET. We've been really lucky to work with Anderson Ruhoff and his team in Brazil at the Federal University do Rio Grande do Sul, and we'll be working with Anderson. Anderson will be leading an effort to start to develop a pilot program for OpenET for Brazil. So those are a couple that I'm aware of, and I'm sure there are others, either in development or available for other regions.
Okay, question 13 is, with the example of the farmer that has saved water using OpenET, has he archived the decrease in use because he has supplied water only for the plant and not for the underground? Can you explain which component of the ET equation he has decreased?
Great, yeah, great question. And I should have said a little bit more about this. Really good question. So a couple of things here. What the farmer did was adjusted what Mark Owens did was when he updated his irrigation system, he adjusted the design of the system to match so that the water applied was matching the ET, the maximum ET rates in each month based on recent data from recent ET data over that field. And what the objective of data-driven irrigation management is to match the amount of water applied to the amount of water that's being removed from the root zone and transferred to the atmosphere through evapotranspiration. And so, yes, the goal there would be to reduce leaching other than the amount necessary for salinity management to flush any salts. And so to minimize that leaching. Now, a couple of things about that. So for farmers like Mark, the key advantage is that actually reduces the pumping costs, or reduces the electricity cost to pump water to supply that irrigation. So that's really the key benefit, is the cost savings for electricity. Some of our partners, Michael Kahn here in the Salinas Valley with the University of California Agricultural and Natural Resources Institute, have also shown that if you couple the irrigation management with fertilizer management, you can also minimize leaching of fertilizer below the root zone. And if the nitrate content in the soil, for example, is being measured with those cheap, easy soil nitrate quick tests, you can also reduce the amount of fertilizer applied by as much as 50%, just because you're minimizing the unintentional loss below the root zone. So those are some of the key benefits. Now, in terms of what happens to the evapotranspiration when you improve irrigation efficiency, that's a really interesting question. And one thing that can happen when you improve the efficiency or design of an irrigation system, and we've seen this in a couple of fields where folks have switched from flood irrigation to those low elevation precision application, those really high efficiency center pivot sprinkler-based systems. When you make that switch, you can actually see such an improvement in the overall consistency of the crop that you are going to get, the grower will get higher yields, but because you have a more consistent, uniform crop, we can actually see evapotranspiration go up. So even though the yield per amount of water applied goes up, the overall total evapotranspiration can go up, even though the amount of water applied goes down. And so when we look at programs to improve irrigation efficiency, and we want to understand the impact to the overall water use, consumptive use within a basin, it's really important that we combine information on changes in applied water on irrigation with changes in evapotranspiration to understand those trade-offs. So gains in irrigation efficiency, meaning that you're doing a better job of matching applied water to ET, don't always translate to reductions in evapotranspiration and consumptive use. So that's a really important point and one of the key reasons to use data from OpenET as we're tracking changes or evaluating impacts from programs to advance water use efficiency across the West. So I know that was a long answer, but that's a really good question.
So next one is about forest management. In that example, I have not understood what they have done to get a more resilient forest. Can you explain all the actions that they have done and which action was justified by OpenET data?
Sure. So in that case, what they are doing is going in and doing mechanical thinning and removal to reduce some of the understory, and then those really dense stands where you have a lot of young trees, actually taking out some of the trees to provide more space and reduce competition, especially for water there in the upland parts of the forest. And so they're doing that already. So they're doing that to try to reduce wildfire risk. What they're using OpenET for is to understand how that's changing patterns in evapotranspiration and also looking for indications of reductions in evaporative stress, water stress for the remaining vegetation. So there's two questions. One is, you thin the forest, is that going to reduce ET? And as a result, you would expect there to be increased runoff. And two, as they try different approaches to these different forest treatment practices, do they see indications of reductions in evaporative stress using the ET data? So they're not, the data from OpenET isn't driving at this point, is not driving the design of the forest management practices and the thinning practices. It's really helping them evaluate the impacts of different practices to see which of the different treatments is going to most cost effectively help them achieve their goals for management of that watershed and protect the water resources.
Great. Next question is, it would be incredible to replicate this for my own country. I wonder what the resources needed would be, and what are the essential data variables, and what's the global coverage of satellite data?
So Landsat is global. We do get an observation from Landsat. Well, each Landsat satellite gives us an observation every 16 days. We have two in operation, Landsat 8 and Landsat 9, so we get an observation every 8 days. Areas that have really frequent cloud cover, daily cloud cover, near daily cloud cover in the morning during certain times of the year. That's one of the key challenges we're working to overcome, either through combination of some of the coarser resolution thermal products from VIIRS with Landsat. I'm also looking forward to the launch of the Trishna satellite and the SPG satellite in the future, looking at incorporating data from EcoStress into OpenET to help us overcome some of these challenges around cloud cover for key areas around the world. The list of essential data variables is long. That's described in that OpenET manuscript in Jara. I'll send the link to that paper to Amita so she can include it in the notes. But if you just search melt in scholar.google or another similar location, melt in OpenET Jara, it should come up. The key thing we would need internationally is the meteorological measurements to help us compute the reference ET. And so having access to data from agricultural weather stations in in or near conditions that are similar to reference conditions for the ASCE Penman-Monteith equation is really helpful to help us assess and identify any biases when we compute reference ET from regional or global gridded meteorological data sets. So that's one of the most important things, is having accurate local weather data from well-maintained weather stations in agricultural areas.
The next is, how is KC value calculated by NDVI?
So the steps used within SIMS are to take the NDVI and first calculate fractional cover, and then to calculate a density coefficient following the approach developed by Luis Pereira and Rick Allen. There is a detailed description of the equations used in that process in that paper that we published in 2020 with Luis Pereira. And so in agricultural water management, I will provide the link for that paper, and that's probably the most time efficient way to answer that question. I also gave a talk on that approach for an FAO series on remote sensing of evapotranspiration. I think that's available online, and so walk through all of the steps done to compute the KC from NDVI. But the paper by Luis Pereira walks through all of the steps and equations used.
How do you think this method will perform with sparse vegetation?
So we definitely see greater disagreement amongst the models in those sparse vegetation. The really arid shrublands, that's one of the areas where we have highest uncertainty. I mean, the models typically agree that the ET is low, but just how low is one of the places where we have the largest disagreement amongst the approaches. So so the uncertainty, again, as a percent of the absolute ET value, is likely to be higher, quite a bit higher than it is over irrigated agricultural lands. We're currently quantifying the accuracy with the OpenET collection 2, since some of the teams made improvements for that particular situation for their models, that particular land cover type. So we'll have updated information on the accuracy for shrublands and other sparsely vegetated areas here shortly. But in general, would expect, again, they'll do a good job of detecting that the ET is low, but would expect higher uncertainty relative to the absolute measurement of ET. So just as a percent error, we would expect higher errors because the ET is low to begin with.
So we can take a couple of more questions, and I know there is a long list that what we will do is try and address as many as we can and then post the answers online. So the next one is, at this point in its development, would you say that the OpenET estimates of open water evaporation are better than using other existing gridded ET estimates?
I'll be honest, I don't think we can say yet. I don't think we can say it. We need to do additional comparisons to see how they compare against pan evaporation and against calculating it from gridded, directly from gridded meteorological data products. We're looking to Hulin Gao's project, and Justin Huntington from the Desert Research Institute is involved with that work to help determine what the best approaches are for quantifying evaporation from open water. So hoping to have some of those answers here soon.
So there's one more question. Are there experiences or examples, I believe, of the OpenET project in the rain-fed conditions in United States, 17 states that you showed?
Yeah, some of these, yes. In terms of the accuracy assessment, yes, we certainly had more than a couple of towers there in rain-fed agricultural fields. So results there were generally comparable with the irrigated agricultural lands. We have some sites over rangelands, so yes, would expect accuracies to be similar. The paper, the OpenET paper, also has a table that lists all of the sites used in that initial phase 1 analysis. So there's also the breakdown site by site, and the OpenET phase 2 manuscript will also include that site by site information. We don't have any use cases at the moment in over rain-fed agricultural lands, but certainly interested in developing some of those to understand just to help confirm the utility of OpenET for quantifying total evapotranspiration over rain-fed lands. We're also looking at rain-fed lands as a way to help us potentially automate some of the calculations of, or serve as a reference in developing techniques to automate the calculations of effective precipitation.
Thank you. Have you tested this technology in arid desert environments? How does accuracy behave in different environments like deserts versus forests?
So I'll just say the same answer that I provided earlier with regards to shrublands. The OpenET will do a good job of, especially that ensemble value, of detecting that the ET is low, but the absolute accuracy, will probably be within plus or minus, half a millimeter per day. But again, the relative accuracy will be higher just because the ET values are so low. So when you have a low ET value, even a small error is going to result in a high % error.
Wonderful. In general, what is the relation between ET and amount of irrigation water? If ET goes up, should I reduce the crop water?
So in general, of course, when we see more irrigation, we will see higher ET, and when things are underwater or deficit irrigated, we'll see reduced ET. The short answer to if ET goes up, should I reduce the crop water? No, not necessarily, and generally not. ET from a well-watered field with minimal soil evaporation is going to represent the biological demand for water for the crop. So the ET can provide a target for the amount of water that needs to be applied. Higher ET definitely does not mean that water is being used inefficiently, right? And so orchard crops, vineyard crops are going to typically need more water over the course of the year because they have to be irrigated, at least during the period where the trees and vines are actively growing. So no, increasing ET does not mean that irrigation needs to be reduced. Instead, the ET can provide a guide for the amount of water that needs to be applied to replace what's being transferred from the soil to the atmosphere. And so in that sense, it can provide a valuable guide for ET. Now, in practice, growers also have to account for distribution uniformity, leaching fraction, if they have sandy soils or heavier clay soils. So all of that's going to factor into the relationship between ET and the amount of water that needs to be applied for irrigation, which is one of the reasons that rather than trying to develop our own irrigation scheduling tools, our approach has been to develop the API and data services so the data can be integrated with with some of the existing tools to support irrigation and nutrient management that have already been developed.
Great. So I think let's make this our last question for now, because it's past our webinar time. Whatever questions remain, we will answer them and post them. So the question is, how accurate are ET data when the agriculture fields are switching from intensive agriculture to agroforestry or equivalent, mixing trees with different cultures?
We haven't tested that particular that particular practice where we're seeing fields switch to agroforestry. In general, I would expect we have a pretty good handle on what the ET is for agricultural fields. We'll have a good handle on it for different types of forested land covers. So I would expect the accuracies to follow that. And so I think we could characterize the accuracy using the data that's already been collected. But we have not looked at that particular situation where someone is switching to from some type of irrigated agriculture to agroforestry. And then I'll quickly answer the last question there about, are you going to use eco-stress data for OpenET? The teams are currently, a couple of the modeling teams are evaluating eco-stress to see if we will, just to make sure it's going to provide an improvement in the overall accuracy of the current models that will enough of an improvement to support this software engineering time required to incorporate EcoStress into OpenET operationally. Another key challenge for us is we're trying to ensure that data will be consistent over the long term. So when the satellites are coming in and coming out of their of operations, we want to be sure we have a graceful way to integrate new missions, but still ensure that the data will be consistent over the long term. So that's a key active area of applied research for the OpenET team.
Okay, great. Thank you so much, Forrest, for your time and for not only this wonderful presentation, but answering all these very interesting questions. And in spite of your busy schedule, you took your time for the presentation and question answer. That's just great. We really want to thank you for that. Also want to thank ARSET team, my colleagues Sean McCartney and Erika Podest. They help co-organize webinars. Also, Brock Blevins, Jonathan O'Brien, Sarah Kashal. They are also organizers of this webinar, and thank you for your help as well. Thank you all for attending today's session. All the material will be available from the website soon, in a day or so. And we'll see you next week at the same time on 8th of June. And at that time, we'll focus more on EcoStress ET. So thank you again. Thanks, Forrest. And thanks, everyone.
Yeah, thank you all for the excellent questions. Thank you all for your time. I really enjoyed talking with you today. Thank you.